Hi everyone, and welcome to the last chapter of this course, where we're going to talk about error handling. This is a difficult topic to cover because there are many solutions available, and the best option highly depends on the context. For example, what kind of application are we working on? Where does the error occur? What should we do when it happens? Should the program crash immediately, or do we want to recover gracefully? All these parameters will influence our decision. So in this chapter, I will present various solutions to the most common problems and discuss their pros and cons. However, I may not cover your specific use case, which means that you will need to experiment and adapt what I present. Okay, so let's jump right into it. First of all, what do we call an error? In this section, I'm talking about runtime errors, meaning that when we execute the program, something goes wrong. We are not on the happy path. So what can we do in this case? There are three main strategies. One, we can fail early, meaning that we stop the entire workflow when we encounter an error. This is the most common scenario. Two, we can accumulate errors, meaning that when there are several issues, we want to know them all. For example, when we receive a request, we may want to validate all fields in order to know which ones are invalid. Finally, we can have a mixed result, something that is partially successful and partially wrong. For instance, if we send an invite to many users, the operation might work for some users, but fail for others. Then, when we encounter an error, we can either report it to the end user or to an internal system, or we can try to recover from the error. For example, we can retry an operation or use a fallback strategy. For instance, if we can't send a message by text, we may try to send an email instead. Now let's have a look at the tools we have in Scala to trigger and handle errors. We have seen a few so far. First, we have exceptions. Whenever we encounter a situation we don't like, we can throw an exception which interrupts the program immediately. For example, here I define a function checkout which moves an order from draft status to checkout status. There are two requirements for this function to succeed. The order must be in draft status, and the basket must contain at least one item. If any of these conditions are not met, we throw an exception. If we want, we can make the code slightly more readable using the method require. As you can see, exceptions are extremely simple to use because they are an escape hatch. They don't impact the function signature. On top of that, when we throw an exception, the JVM provides a stack trace to help us debug where the error occurred. Here we can see that the exception happened inside the method require at line 340 of predef.scala, and we can also see that require was called by the method checkout at line 41 of order.scala, and so on. So exceptions are really convenient, but they cause lots of maintenance headaches. This is because the signature of the function doesn't tell us if the function can fail or not. So we can't rely on the compiler or an IDE to warn us if a method is unsafe. The only way to know is to check the implementation, which is not foolproof because we may forget to do it. And even if we do remember, the implementation may change in the future. Additionally, even if the function can fail, we don't know which type of exceptions it will throw. For example, here I created two subclasses of exception, one for each error scenario. Then let's imagine that in some part of our codebase, we want to ignore the error when the basket is empty. To do that, we need to read the implementation of checkout to know that in this particular case, we throw an empty basket error. This is fine when we implement the functionality the first time around, but again, it leads to bugs and inconsistencies when the program evolves. In that regard, Java offers better documentation tools with check exceptions. Checked exceptions are visible in the signature, and they force the caller of the function to handle or propagate the errors. Though check exceptions are not perfect, they also bring their own problems. Finally, the last issue with exceptions is that they interrupt the program immediately, which is a good default behavior, but it's not always what we want. For example, createUser validate that the name of the user is not empty and that they are at least 18 years old. Now, if we call createUser with an invalid name and an invalid age, we only get an error for the name. This is because this function blows up immediately when the first exception occurs. So for all these reasons, I recommend limiting the usage of exceptions as much as possible, especially if you work in a medium or large code base. Then, in Chapter 5, we saw another way to handle errors, using the I/O data type. We saw that an I/O is a description of an imperative program, which means that an I/O is an immutable object, it doesn't do anything. However, when we run an I/O, it executes an imperative program, which can throw an exception. This means that we can transform any code that uses exception to I/O relatively easily. First, we need to replace throw with io.fail and wrap all successful code with io.apply. Then we need to change the return type to be io of A instead of just A. The latter is the main advantage of this technique. Now we can document if a function can fail or not. If the function can fail, the return type will be io of something, but if it cannot fail, the return type will be without io. So I/O partially solves the documentation issue of exceptions. I say partially because we have limited information about the error. We only know if a function can fail or not, but we don't know which specific type of exceptions will be thrown. Some I/O libraries, such as MonixBio and Zio, resolve this issue by adding an extra type parameter to customize the error type. The first type parameter describes the type of error when the I/O fails, while the second type parameter describes the type of value when the I/O succeeds. For example, we can create an I/O which only fails with a user not found error. The nice thing about this approach is that we can still use throwable as an error type, but if we need to, we can use something else instead. As a side note, we can also use a special type nothing to describe an I/O which cannot fail. For instance, getTime reads the current time from the system, and we know that this action is always successful. Now, I/O is not perfect either. First of all, I/O tends to spread inside a code base. Indeed, if a function returns an I/O, all functions that calls it must also return an I/O. For example, if addItems and checkout return an I/O, then order workflow must do the same. I/O also requires us to add some boilerplate to combine them, such as using flatmap or for comprehension. Most importantly, I/O is too powerful. For example, checkout is a deterministic function. For all inputs, we always get the same output, and it doesn't contact an external system. Checkout is a pure function. It takes an immutable input and returns an immutable output. The only issue is that the input may not be in the correct state, in which case we need to reject it. So we could use I/O for the job, but it would be overkill, as we wouldn't be following the rule of least power. And this is not a theoretical concern. We have seen in the previous chapter that testing a pure function is much simpler than testing one with I/O. So what else could we do? I'll let you pause the video and think about it for a minute or two. So the big idea behind functional error handling is to encode errors as normal values, and then change the output type so that it combines success and failure values together. In other words, we want to say that the function returns a success or a failure. How we encode this OR relationship is going to be the main subject of this chapter. In Scala, we have many types that fulfill this purpose, each with their own specific use case. You have probably heard of some of them, like option, try, either, validation, and I/O. The first three types are in the standard library, while the last two are in functional libraries like cats or ZO Prelude. Great, so I suggest that we take a break now, and in the next few videos we are going to cover most of these error types. The goal is that by the end of the course, you will be able to use the most appropriate error type for the task at hand. See you soon, everyone.